Our next speaker is Ben Bakker from University of Illinois at Chicago, and he will tell us about Baily Borel compactifications of period images and the b-semiampleness conjecture. Ben.
Perfect. Thank you. Thank you so much for the introduction and the invitation. Sorry I couldn't be there in person, but yeah, it's a real pleasure to help celebrate sort of the influence of Spencer, who in fact was my mathematical great grandfather, I think. So I'll be talking about some ideas that are closely related to sort of the moduli of algebraic varieties, which of course has been greatly influenced by Spencer's work. So before I begin, this is all joint work with Stefano Filipazzi, Mirko Mauri, and Jacob Tsimerman. And I'm going to be talking about sort of analogs of Baily-Borel compactifications in some other settings. So let me first summarize the very beautiful kind of classical picture of Baily-Borel compactifications, which goes back to the 50s. So the easiest classical story is for moduli of abelian varieties, which as an analytic space are very concretely sort of Siegel upper half space, some higher dimensional version of the upper half plane, modulo the action of symplectic 2G by 2G matrices, integral symplectic 2G by 2G matrices via Mobius transformations. And this is extremely concrete because given the data of a point in the Siegel upper half space, you can actually build the principally polarized abelian variety up to this freedom that is encoded by sort of the action of up to the freedom of choosing a symplectic framing, which is what this modulo of this symplectic group is to account for. Now, connected to some ideas coming from sort of reduction theory, in 56, Satake was led to the introduction of a topological compactification of this complex analytic space. It's easy to see that this complex analytic space is not compact. And compactifications are always useful, especially if they're sort of meaningful. And he introduced this topological compactification by sort of adding all the AGs for smaller g into the boundary. Okay, and this had some motivation, again, coming from reduction theory. I'll explain the kind of geometric motivation in a second. But he introduced this topological compactification and suggested that it should be the topological space underlying a compactification of AG as a complex analytic space, so that this topological space should naturally have the structure of an analytic variety. And this was confirmed shortly thereafter, and then some, by Baily in 58, who in fact showed that this topological compactification is the topological space underlying a projective algebraic variety. So even better than just a complex analytic space. And he did this by showing that this compactification is the topological space underlying proj of a certain graded ring of automorphic forms. So he very much was using sort of the theory of automorphic forms on Siegel space. Okay, so in particular, in retrospectively, this implies that that AG, just the open space of smooth principally polarized abelian varieties, has a natural structure as an algebraic variety, which was not known previous to that. Now, I said it's particularly useful to have sort of meaningful compactifications of a modular variety. And I don't exactly know what the date to attribute this to, but there is a modular interpretation to this compactification coming from the theory of neuron models, which Ludmila referenced in her talk. If you have some experience with Baily-Borel compactifications, you know that they're sort of quite singular at the boundary. So it's too much to hope for that there's a reasonable universal family of sort of degenerating abelian varieties. But the sort of upshot is that limits along curves do make sense in a reasonable way. So let me just describe that modular interpretation in some detail. So the picture is as follows. So I'm going to start with a family of principally polarized abelian varieties over some punctured curve, let's say, some algebraic curve C. And let's say I remove 1 point from it to get C circle. And I'm going to have an actual family of polarized abelian varieties over that. The neuron model gives you some particularly nice way of taking a sort of relative compactification of this family. So that's what Z is. I start with this family over the punctured curve, and I take the neuron family over the completed curve. Strictly speaking, I want to take the semi-stable neuron model, so you may have to pass to some sort of finite cover, possibly ramified, of C. And now this special fiber, one of the nice properties of the neuron model is this special fiber of this part of this completion has the structure of a group variety. In particular, the identity component is a semi-abelian variety. And semi-abelian varieties are always extensions of compact abelian varieties by tori. And so the compact part, the identity component of the neuron model, gives me, it turns out to be principally polarized. It gives me a lower dimensional principally polarized abelian variety. And that's exactly the point in this compactification that I limit to. Okay, so as far as one parameter degenerations of abelian varieties are concerned, the point in the boundary you land up in is exactly the sort of compact part of the semi-stable neuron model. So that's a pretty decent modular interpretation. And like I said, it has some interpretation in terms of the reduction theory of the corresponding quadratic forms. Well, I mean, we see manifestly from part 2, since this compactification is proj of a finitely generated ring, it comes with a natural polarization. This polarization has some geometric meaning. So if I consider the universal family of abelian varieties over sort of the open part where the abelian varieties are not degenerating, there's a natural line bundle with some positivity properties. What is it? Well, I basically take the relative one forms and take the push forward and take so this gives me some vector bundle, and I take the determinant. This gives me some line bundle on the open part, which it turns out extends to an ample line bundle on this compactification up to a power. I'm going to basically systematically ignore these issues of up to a power. And indeed, I mean, these automorphic forms that Baily used to give a projective algebraic structure to this compactification are exactly the sort of sections of this automorphic line bundle with some controlled behavior at infinity. I meant to say at the beginning that I put a handout version of these slides on my website. There's a slide page, because I know with slide talks sometimes it's annoying that you sort of can't go back. So if you do want to go back to a previous slide, you can look at the slides on my webpage. Okay, anyway, so there's a natural ample line bundle on this projective compactification. In fact, this compactification satisfies a sort of minimality or universality property with respect to this line bundle. In a sense I'll make precise in a second. So this was established by Borel in 72, called Borel extension. And the setup is as follows. So suppose x is smooth and d is a log smooth divisor inside of x. And suppose I have a map to the open part, so an actual family of principally polarized abelian varieties over the complement of the log smooth divisor. Then the kind of minimality property of this compactification is, in this situation, whenever I have an actual family over the complement of a log smooth divisor, the corresponding map to the modular variety extends to this compactification. So there exists this extension f bar. And moreover, this extension is compatible with the line bundle in the sense that on the one hand, we had the natural line bundle coming from the universal family on AG, and we saw that it extended to this compactification. On the other hand, you can also, in the log smooth situation, there's a natural extension of this line bundle over the SNC boundary. One way to think of that is in terms of the description I gave you. I told you that this line bundle comes from, if you have a family of abelian varieties, you take the push forward of the one forms, you take the vector bundle of one forms and take its determinant. And in the log smooth situation, like when your base is log smooth, you can imagine you can take a semi-stable model for your family of abelian varieties and then push forward log one forms. And it turns out that gives you a natural extension of this line bundle. I'll call that LX. You can also use sort of Hodge theory to talk about this extension. I'll use that in a second. So on the one hand, you have a sort of a natural extension of the same line bundle coming from two places, one going from AG to this Satake Baily Borel compactification, and the other going from the complement of the log smooth divisor to X. And they agree. Okay, so sort of in words, this is saying that if you look at maps from log smooth varieties, which come from having an actual family on the complement of a log smooth divisor, then the map completes as a map to this compactification in a way that's compatible with the two natural extensions of the line bundle. Okay, so that's why I call it a minimality property, because somehow the complement of an SNC divisor always completes to a map to this compactification. And in fact, it's even better. So I phrase this in terms of sort of a universality property for maps from the complement of log smooth divisors in algebraic varieties. But there's an analytic version. So we even have this same universality statement, but in the analytic category where x comma d is just replaced with a polydisk, and the divisor is just the union of coordinate hyperplanes. And of course, that's strictly stronger than the algebraic case because it implies that. Okay, so that's a summary of all the nice properties that this Satake Baily Borel compactification of AG has. And shortly after the work of Baily, Satake generalized his work to give a topological compactification of any any arithmetic locally symmetric variety. Okay, so the quotient of a bounded symmetric domain by an arithmetic lattice. And then that was shortly thereafter Baily's work was generalized in 1966 by Baily and Borel to give a projective compactification of these arithmetic locally symmetric varieties. So in the general case, these compactifications are called Baily-Borel compactifications. Okay, so that's the classical story. It's very much connected to sort of abelian varieties and automorphic forms. And is kind of specialized to the case of quotients of bounded symmetric domains by arithmetic lattices. Sort of around the same time, Deligne and Griffiths were sort of generalizing this picture to any smooth projective variety. So again, I'll take x comma d to be a log smooth proper pair. So x is a proper algebraic variety and d is a log smooth divisor inside a simple normal crossings divisor inside of x. We can take any smooth projective family, any family of smooth projective varieties over the complement of that SNC divisor in x. And we can consider the local system we get by thinking about the degree k cohomology of the fibers. Okay, so that's a local system by Erasmus's theorem. This is a topologically locally trivial fibration. And this local system comes equipped with a polarizable Z variation of Hodge structures, which I don't want to spend too much time on. I'm sure probably most people know what this is, but I at least want to say that a piece of this is that there's a certain filtration on the associated flat vector bundle, the vector bundle with connection associated to this local system. And that in particular means I can track how this filtration is moving with respect to the flat structure. And this gives me an analytic map, a complex analytic map from the base X circle into a moduli space of filtrations on a fixed vector space, which I'll call d mod gamma. Really, it's a sort of the moduli space of Hodge structures modulo the monodromy of this local system. And so this is just an analytic map to an analytic space. This d mod gamma you should think of as being like the upper half plane, the Siegel upper half space. This is kind of like Siegel upper half space modulo the symplectic group, except importantly, in this more general setting, it's never algebraic. This was proven by Griffiths, Toledo, and Robles. Griffiths, Robles, and Toledo. Sorry, I got my alphabet wrong. So this is in general, we can't, it's a more complicated question to ask whether there are certain kinds of compactifications here of d mod gamma, because it has no chance of being an algebraic compactification. What we can do instead is consider the image of this map. Now, this is an analytic map. The image is not necessarily super great, but Griffiths proved that, in fact, this map is always relatively compactifiable. So it always can be embedded inside of a proper map, which means that the closure of the image of this analytic map is actually a reasonable complex analytic subspace, not necessarily compact, of course, because it was only a relative compactification. But this image is some complex analytic space. And Griffiths asked in his ICM address in 70 a number of questions. Basically, to what extent does this curly Y kind of mirror the behavior we saw with AG? So more pointedly, is this curly Y algebraic, first and foremost? Second, there's a natural line bundle, which is similar to the automorphic line bundle we discussed before. And so we call this the Griffiths bundle. It's basically you take the tensor of the determinant of all the filtration pieces in this filtered flat vector bundle that I referenced before. This line bundle is sort of for curvature reasons. It has a natural metric with positive curvature, so you ought to expect that it might be a natural polarization. Of course, in order for it to, before we can even ask if it's ample, we have to ask if it's algebraic. So first, is it algebraic? And once if it's algebraic, is it ample? And then finally, is there some version of the Baily-Borel compactification of this curly Y, assuming A and B are true? Okay, so that sort of has all of the properties, 1 through 5 prime that I mentioned at the very beginning. Okay, so as far as questions A and B are concerned, these were resolved a number of years ago now, although it appeared in print in 2023. This is a theorem of myself, Johan Brunebarb, and Jacob Tsimerman, which says that the answer to question A and B is yes. So basically, this whole part of the diagram that I wrote over here is algebraic, in fact, uniquely algebraic. So that part of the diagram is the analytification of some algebraic arrow. So in particular, Y is algebraic, and the map from X circle to Y is algebraic. And the line bundle is again uniquely algebraic. And moreover, that line bundle with its unique algebraic structure is ample. Okay, great. So that pretty definitively answers questions A and B. So the main results I want to talk about today is the resolution of C. So the existence of this Baily-Borel compactification. And indeed, it's going to basically have all the properties that we wanted it to have. So here is at least a precise statement. So this is theorem 1. So remember before Baily got the Baily-Borel compactification of AG by taking proj of a finitely generated ring of automorphic forms. And of course, you have to, before you get a finite, before you get in each grade a finite dimensional vector space of automorphic forms, you have to control the behavior at infinity. If you just take all automorphic functions, that's too many. Similarly, here we want to get a finitely generated ring of sections, and in each graded piece, in order for that to be a finite dimensional vector space, I can't take any sections of the kth power of this Griffiths line bundle on Y, because Y is not proper. So we take, that's what the subscript mg is. So it's the moderate growth section. So these are sections that have moderate growth with respect to the Hodge metric, which I don't, whatever. If you don't know what that means, then we don't have to get into it. But the point is that you specify some condition which gives you a finite dimensional space of sections and for each k. And then this graded ring we show is finitely generated. And okay, you have a finitely generated graded ring. You can therefore take its proj. And taking proj of this ring gives you a projective compactification of the image of the period map, what I was calling Y before. And it's one to which the Griffiths bundle Ly extends, and it extends amply and universally, as in the statement of Borel extension. So as in what I was calling 5 above. And in fact, even the analytic version, 5 prime, which is the same statement over polydisks. Okay. So this compactification will once again have the same minimality property in the sense that any map from the polydisk will extend. The polydisk minus the coordinate hyperplanes. Okay, so just I referenced a couple of the properties of the Baily-Borel that I mentioned at the beginning. So let me just talk about a couple other things. Before I do that, actually, let me just kind of informally deduce a corollary, which is basically that one reason period maps are useful is there are sort of many algebraic varieties which have an immersive period map, right? So it's not gonna, and that basically tells you that there are many algebraic varieties for which deformations of the variety can be tracked, can be read off, at least formally, from how the Hodge structure is deforming. So in other words, the moduli space embeds into the D mod gamma, even if the full D mod gamma is not algebraic. And this theorem will tell you that any moduli space that has a local Torelli theorem, so that's what I mean by has an immersive period map, has a canonical minimal Hodge theoretic compactification. Okay, well, just as I was describing before with AG, it's kind of useful for the boundary that we add to have some kind of modular meaning. And that will be true for these compactifications in essentially the same way, in kind of the analog of this neuron model picture I was describing. This compactification will be stratified by subvarieties, each of which are very close to sort of images of period maps that can be extracted from the degenerate variations of Hodge structures. Okay, so for the experts in the audience, basically, if you take the associated graded of the limit of its Hodge structure, that gives you a period map on each stratum of the boundary. And the boundary pieces of this Baily-Borel compactification will essentially be the period images of those up to some finite maps, which sort of are forced on you by the kind of global geometry of the boundary. But this specializes to exactly the picture coming from neuron models, because the compact part of the identity component of the neuron model is exactly the relevant piece of the limit mixed Hodge structure. Also, so there's been a lot of previous work in the circle of ideas, especially by Green, Griffiths, Laza, and Robles, and Green, Griffiths, and Robles. And I specifically want to highlight that, and so there are some special cases like the two-dimensional case, as well as some specific moduli problems that Laza has looked at. I specifically want to mention that the paper of Green, Griffiths, and Robles establishes a sort of a key ingredient in the proof that I'll talk more about later in the proof of our theorem. Okay, so any questions? Okay, great. Please feel free to shout out questions because I can't see the audience from here. All right, so that's nice. If That's nice, but somehow it tells us something about the Griffiths bundle. There are lots of semi-positive line bundles that arise from Hodge theory. Okay, so if on the complement of a log smooth divisor, I have some polarizable Z variation of Hodge structures, as before. This theorem I just mentioned, giving a Baily-Borel compactification of the image of the period map, in particular tells you that this Griffiths bundle is semi-ample. Okay, so it tells you more than that, but one thing you can extract from that is that this line bundle, which, as I mentioned before, is semi-positive. And if you restrict to the image of the period map, it's actually strictly positive. But on X, it's semi-positive, and so you then therefore might expect it to be semi-ample, and that's indeed what theorem one will tell you. But if I take the determinant of any piece of the Hodge filtration, that will be semi-positive. So it's kind of a natural question, okay, well, when are those semi-ample? Semi-ampleness of line bundles is kind of important in algebraic geometry because it means that there is some morphism, some contraction, along which that line bundle is pulled back and on which it's ample. So it sort of encodes kind of fibration structures. Unfortunately, it's not always true that these line bundles are semi-ample, which somehow makes it even more interesting because, can we come up with a good criterion for when it is semi-ample? Because there are interesting cases in which we would want to know its semi-ampleness. And indeed, there are some important cases where one would like to be able to show that it's semi-ample. So I want to talk a little bit about how we kind of generalize our picture to be able to address that question. And there's a special case, namely if my variation, if the deepest part of the Hodge filtration is already rank 1, okay, then I don't need to take a determinant. Oops, where is it? Oh, here. I don't need to take this determinant because it's already rank 1. It's already a line bundle. So in that very special case, we call the variation a Calabi Yau variation of Hodge structures for reasons that'll become apparent in a second. And we also give a special name to that deepest part of the Hodge filtration. That's a line bundle. We just call it the Hodge bundle. Okay. So like I said, this is kind of a special, considering this Hodge bundle is like a special case of considering these determinants. But actually, it's the general case because we can always, for any variation of Hodge structure, if we take an appropriate wedge, we will get a Calabi Yau variation whose Hodge bundle is exactly the determinant that we were originally interested in. Okay, so these determinants that I referenced above, these semi-positive determinants, are always the Hodge bundle of some auxiliary Calabi Yau variation. And in fact, the same thing is true for the Griffiths bundle itself, right? This Griffiths bundle was the tensor of all the determinants, which was cooked up because it's always strictly positive. And that is nothing other than the Hodge bundle of some other auxiliary Calabi Yau variation, namely the tensor of all of these wedges. So actually, this question about when Hodge bundles of Calabi Yau variations is semi-ample completely deals with all cases of this question of determinants and their tensors when they are semi-ample. Okay, finally, I promised I would explain why I call this a Calabi Yau variation, and that's because there's a very particular case coming from geometry where we are particularly interested in whether this Hodge bundle is semi-ample. And that is the case of if we take a smooth projective family of Calabi Yau, let's say M folds. Okay, so Ludmilla was talking a little bit about Calabi Yau, specifically about hypercalars, but any smooth projective variety with trivial canonical bundle is called Calabi Yau. And if we take the middle cohomology such a manifold, it's the deepest part of its Hodge filtration will be rank 1. Okay, and that push forward of the canonical bundle kind of shows up, plays a particularly important role in geometry, and that's what ends up being the Hodge bundle in this case. Okay, so that's why that is one particular example where we are specifically interested in this slightly different question of when a slightly different line bundle is semiample, as opposed to the Griffiths bundle, which theorem 1 tells us is always semiample. Okay, so that was a lot of discussion to motivate the following theorem, which answers the question, when is a Hodge bundle semiample? Like I said, this is a strictly more general question than when is the Griffiths bundle semiample, for which the answer is always. And that's theorem 2. Theorem 2 says, okay, so suppose I have, once again, a proper log-smooth algebraic space, and suppose I have a variation of Hodge structure on the complement of the S and C boundary, which is a Calabi Yau variation of Hodge structure. So it has, its lowest Hodge filtration piece is rank 1. We call it the Hodge bundle. Then the Hodge bundle is semiample, so we give an if and only if criterion for when it's semiample. It's semiample if and only if it is integrable and has torsion combinatorial monodromy. Okay, so let me describe what those mean. So the integrability question condition is easier to state, and also it's you'll see why it's called integrability. Basically says the following. So if you have some analytic germ inside of X, and this Hodge bundle, which remember is a sub-bundle of the ambient flat vector bundle, the local system. If you have some germ along which the Hodge bundle is flat, then it's also flat on the Zariski closure of that germ. Okay, so this is precisely some like algebraic integrability statement about the foliation along which this Hodge bundle is flat, whether that's algebraically integrable or not. Okay, so that's the integrability condition. It's easy to see, I won't get into it, but it's easy to see that this is automatic for the Griffiths bundle. Second, this torsion combinatorial monodromy condition. What does it say? Well, it says that if you have some connected curve, so you should imagine some like loop of curves like this. So if you have a loop of curves on which this Hodge bundle is numerically trivial, so in other words, it's degree 0 on each component, that doesn't necessarily mean it's torsion, because there could be some combinatorial monodromy. So the statement of torsion combinatorial monodromy is that whenever you're in this situation, whenever you have a loop of curves on which the Hodge bundle is degree 0 on each factor, then in fact it's torsion. And this is the result of Green, Griffiths, and Robles that we need. They show that the Griffiths bundle automatically has torsion combinatorial monodromy. Okay, so that's why this theorem, given these two results, applies immediately to the Griffiths bundle to tell you that it's semiample. Okay, so now let's talk about families of Calabi Yau. So I mentioned that was kind of the geometric motivation for considering this question of when Hodge bundles are semiample. And we were particularly, the motivating geometric example was you have a family of k-trivial varieties, and you look at their middle cohomology, and you look at the push forward of the dualizing sheaf, so the canonical bundle, and you want to know when that's semiample. And this theorem tells you that it's enough to check these two conditions. So theorem 3 is the theorem that in this situation, the Hodge bundle satisfies those two conditions. Okay, so precisely, if you have a proper log smooth base, you have a variation, a Calabi Yau variation on the complement of the S and C divisor, and it comes from the middle cohomology of a family of KLT Calabi Yau pairs. You can ignore the KLT in pairs if you want and just think about smooth projective Calabi Yaus, but it's important that it works in this level of generality. Then the Hodge bundle satisfies these two conditions that we needed in theorem 2. It's integrable in its torsion combinatorial monometry. Okay, so in particular, that tells you that in this geometric situation, the Hodge bundle is always semi-ample, and that allows you to build Baily-Borel type compactifications of the moduli space of Calabi Yau varieties, except that they don't satisfy the universality property with respect to the Griffiths bundle. They satisfy it with respect to this Hodge bundle. Okay, and that will give you a slightly different modular compactification. So I'll just say the corollary here. The core spaces of moduli stacks of smooth polarized Calabi Yau varieties have a canonical Baily-Borel compactification, which we call the BBH compactification to distinguish, the H is for Hodge, and that's to distinguish it from the BB case, which is sort of universality with respect to the Griffiths bundle. This is universality with respect to the Hodge bundle. Other than that, it's basically the same thing. You have a graded ring of moderate growth sections of the Hodge bundle now, not the Griffiths bundle, which is finally generated. And taking its proj gives you a compactification which has the same universality property with respect to the Hodge bundle that the previous one had with respect to the Griffiths bundle. And the long and the short of it is this BBH compactification always kind of lives below the Baily-Borel compactification, because there are going to be some curves for which the Hodge bundle is trivial, but the Griffiths bundle is not trivial, and those curves will be contracted along this map. So it's some further contraction of the Baily-Borel compactification. This is something you don't see in the classical situation, because actually it turns out that the two are the same. Basically, because the Hodge filtration is not complicated enough so that the different determinants give you different things. In the bounded symmetric domain case, there's only one line bundle you can form from the filtration pieces. Okay, so this I stated this for smooth projective Calabi Yaus, but it also works for KLT Calabi Yau pairs, which I don't want to get into. But again, that's important because this is what implies what's called the b-semiampleness conjecture, which is an important conjecture in sort of the minimal model program. This is sort of goes back. There were sort of early formulations of Mauri, and then Kawamata, Shakurov, Ambro, and then eventually there was a formulation from Prokhorov and Shakurov. Which again, I don't want to get into the precise statement, but you can imagine that it somehow follows from the existence of this Baily-Borel type compactification associated to the Hodge bundle. It follows pretty easily from that. I should also say there were sort of partial past results by many people on this b-semiampleness conjecture, in particular Ambro, Lazic, Flores, and many other people. I'm not doing this sort of, despite the fact that my title was half, about the b-semiampleness conjecture. I'm not really doing justice to that topic, both because I'm not an expert in minimal model theory and because, there's only so much time. But anyway, I don't want to throw anyone under the bus. Okay, great. So I want to talk about some ideas from the proof, and let me just lay out the kind of three main theorems. So again, we have theorem 1, which was basically saying you have canonical minimal Hodge theoretic compactifications of any image of a period map, and these were called the sort of Baily-Borel compactifications. Theorem 2 was a more general statement about semi-ampleness of more general line bundles, so Hodge bundles of Calabi Yau variations, which was sort of a specialization of which was this Griffiths bundle. And those two things taken together are connected because, like I said, the existence of these compactifications in particular implies that the Griffiths bundle is semi-ample. And because of this theorem of Green, Griffiths, and Robles, and the Griffiths bundle, the Griffiths bundle always satisfies these two conditions, and therefore it's a consequence of this theorem that it's semi-ample. So in fact, the first step of the proof of theorem 1 is to first prove theorem 2 and then apply it to the Griffiths bundle to get semi-ampleness, and then you do some extra work to conclude the remaining parts of theorem 1. And Theorem 2 and Theorem 3 are, of course, connected because Theorem 3 tells you that in this very particular situation, when you're looking at the middle cohomology of a family of Calabi Yaus, the two conditions that you need in Theorem 2 in order to guarantee semiampleness are true. And so these two theorems together, I didn't know how to draw this arrow, so I'm going to draw it manually. These two theorems together imply that sort of canonical Hodge theoretic compactifications of Calabi Yau moduli spaces exist, which are now minimal with respect to the Hodge bundle, and those we call these YBBH. Okay, so that's sort of the three theorems and how they're related to each other. So in the remaining 20 minutes, I guess, I want to discuss mostly, you can see how sort of theorem 2 is kind of used in both deductions of theorem 1 and in the deduction of this existence of the YBBH. So I want to spend most of the time talking about the ideas from theorem 2, because that's sort of where the main work is. And then at the end, if I have time, I want to explain how you verify integrability and torsion combinatorial monodromy in this geometric setting. So we saw that they were, one of them was automatic and the other was a consequence of this theorem of Green, Griffiths, and Robles. But they're not true in general. And so for theorem 3, you need to actually use the geometry of how Calabi Yaus degenerate to verify those two conditions. And that actually uses some interesting birational geometry. So it's not coming from sort of abstract Hodge theory. Anyway, okay, so I probably won't get to that. So I'm mostly going to talk about sort of how the proof of theorem 2 works. And as usual, in algebraic geometry, sort of semiampleness is somehow very tricky to prove because it's like not a numerical property. There's no Nakai-Moishizan for semiampleness. It's hard using sort of degrees and stuff to differentiate the trivial line bundle from a degree 0 but non-torsion line bundle. And this is why semi-ampleness questions are so much harder. So one strategy, so on the other hand, ampleness is numerically, there is a numerical criterion, right? There's a Nakai-Moishizan. So it's always easier to check ampleness. And so the strategy for proving that this Hodge bundle is semi-ample under these two conditions is to make the map that it would produce if it were ample, right? So if it were semi-ample, rather, any semi-ample line bundle will induce an algebraic map such that the line bundle descends through that map and is ample on the target. So we're going to sort of do that backwards. We're going to prove semi-ampleness by constructing an algebraic morphism with a line bundle on which it's ample, and then and which pulls back to the one we wanted to show is semi-ample. Okay, so we're going to first make that algebraic map. We're going to first make it as a topological space. And okay, well, the topological space is actually pretty naturally determined. I mean, this map, so let me just give some names to things, right? We have X and we want to produce some Y. We want to produce an algebraic map from X to Y, which has the property that this Hodge bundle X is pulled back from some line bundle on Y. And the line bundle on Y has the property that it has strictly positive degree on every subvariety, right? That would imply that it's ample. So what does that mean? Well, it means that the fibers of this map are exactly what's swept out by curves that have degree 0 with respect to mx. There's no other choice. We have to contract every degree 0 curve. And okay, well, that gives a natural equivalence relation on x. Namely, if you have 2 points which can be connected by some connected chain of degree 0 curves, then those 2 points need to be identified in y. Okay, so that gives an equivalence relation R. It kind of has the flavor of the equivalence relation that gives you the MRC quotient, where you want to look at connectedness by rational curves. Okay, so the first thing you want to prove is that this is a proper algebraic equivalence relation. Okay, as soon as it's a proper algebraic equivalence relation, then it means this quotient exists at least as sort of a reasonable space, at the very least of which I mean sort of a Hausdorff topological space. Let me just say, I'm not going to say too much about the proof of this, but let me at least tell you what the subtlety is. It's pretty easy to show that this equivalence relation is a countable union of algebraic things. The issue is that you need to show some boundedness in the sort of chains of curves that connect 2 points, right? So a priori, you might need, to flesh out this equivalence relation, you might need unbounded length chains of degree zero curves, and that would be bad. That would contradict properness. So you need to show that you can bound the length of the chains you need to connect 2 points that are connectable by a chain of degree zero curves of some length. So anyway, so you do that. Okay, so that means you can build this topological space. And by doing some modifications to X, you can in fact further assume that the kind of natural stratification on X that comes from the log smooth divisor descends to Y. I'll draw a picture in a second, but what I mean by that is there is some stratification of Y by locally closed topological subspaces, such that the inverse images of these strata are unions of strata upstairs. Okay, so somehow there's some stratification of X such that, and the things upstairs are all algebraic, and they map in a saturated way down to a stratification of Y. And finally, by this theorem with Barb and Tsimerman on the algebraicity of images of period maps, each of these strata, so I said they were just topological subspaces, but each of these strata is actually algebraic because it's the image of a period map. And the line bundle descends on kind of each piece and is ample on the target. Okay, so the situation we're in is that we have this topological space Y, which we can break up into a bunch of things which we know are algebraic varieties, and the line bundle descends to all the pieces and is ample. And what's left is how to glue them together, which is the hardest part of Baily Borel's theorem too. So it sort of makes sense that should be the remaining obstacle. Oh, I guess I should say, so here to get this descent and this ampleness, here we've used the two conditions. Okay, so let me draw now a picture, right? So we have X, so it looks like this, and we have this topological space Y that we've made. Okay, and I said that maybe after some blowups, we can assume that the stratification on X, after taking unions of strata, map down to Y. So the kind of picture you should have in your head is that we have X. Maybe there's some divisor like this, which gets contracted to a point in Y. And maybe there's some other divisor like this, which gets mapped to gets contracted to like a curve. Okay, and then in this intersection, right, it gets mapped down to there. So this is the kind of thing you could imagine. So we have our quotient map like this. Okay, and what is the game now? So I've said that Y has this stratification such that the inverse images are kind of unions of strata upstairs. Each piece of this stratification has a natural algebraic structure, which is compatible with the preimage upstairs. And the line bundle descends to Y on these strata. Okay. So to glue those, so the main remaining issue, as I mentioned, is to glue those algebraic pieces together and to use the line bundle to do so. And concretely, what does that amount to? Well, basically, like for any point in Y, if I take some neighborhood of that point, I can look at the preimage upstairs. Okay, so that's the preimage of the point. And the preimage of that open set is some tube around that fiber. Okay, and I have my line bundle upstairs, MX. And basically, what it remains to do is to show that locally downstairs, if I look at pre-images, I can find sections of my line bundle on that tube which separates the fibers over points downstairs, right? So I want to produce functions down to, to put an analytic space structure in Y, for instance. I got to produce local functions which separate points. Okay, and the way I'm going to do that is by producing sections on the inverse image of the line bundle that separate points. Okay, so that's the main game, to show that there are sections that exist that separate those points, to separate the fibers up here. And in step 2, which I'm basically going to say nothing about, you use Hodge theory to make some sections like this. So what do I mean by that? Well, okay, well, it's going to erase my picture, but I can at least go back. So precisely near any point on a stratum, we're going to use some Hodge theory, which I'm not going to talk about, to show that there are local sections that separate fibers over that stratum. That's the key property that these sections have. Okay, so just in this picture, just to draw what that looks like, that means that in this neighborhood, right? So I have this neighborhood of a point in Y. That means I can produce sections on this tube upstairs which separate this point from maybe this point, right? So I can separate these two fibers that live over the same stratum. Okay, so that's something. That's good news. It's not the best news, however, because these local sections do not give an analytic structure to Y. Okay, they're not enough to give an analytic structure in Y. Okay, and I want to be very clear about this point. So I'm going to draw four pictures. So here's 1, here's 2, here's 3, here's 4. These are all pictures of Y. Okay, and so, they all have this stratification that I mentioned. And I want to describe 4 possible scenarios. So we might have 2 points, like, let me give some names to these strata. Let's say the biggest strata is Y0, the next smallest strata is Y1, and then the deepest strata is Y2. Okay? So now I might have 2 points in Y0 in a neighborhood around them. Okay, and I might want to produce local sections that separate those 2 points. Okay, so that falls under the category that step 2 is okay with, right? Those are 2 sections, 2 points in the same stratum, and we're looking at an open set of them. So this is okay by step 2. Okay, now I can also look at 2 points on the green stratum and a neighborhood there. Okay, and I might want to produce sections in this neighborhood that separate those 2 points. That's also okay by step 2. That's exactly what step 2 does. Okay, what step 2 does not do is, if I take a neighborhood of a point in this green stratum, but suppose I want to separate 2 fibers off of that stratum. Okay, this is where the gluing would, this is how I would glue the analytic structures. This step 2 does not give you that, right? Because in step 2, you were only able to generate sections that separate fibers above that strata. However, this is still okay, and this is by the theorem with Brunnebarg. So why is that? Well, the main point is that we know that Y0 is algebraic. And actually, we know slightly more. We know that global sections of the Hodge bundle separate points on Y0. Okay, so that means we have sections of the line bundle separating points on Zariski opens, not just on analytic opens like here. And Zariski opens are much bigger, and in particular, a Zariski open will include a neighborhood like this. Okay, so the fact that I have algebraic sections that separate points actually allow me to do this. Okay, and again, if you have experience with the Baily Borel, I mean, you know that kind of the local topology around these strata is quite complicated. So like this is indeed this is a difficult thing to show that you can take, to show that you can take these local sections and kind of patch them up in this complicated neighborhood of the stratum, and that's what the algebricity of why not allows you to do. Okay, but what we can't yet do is this situation. Suppose I have a neighborhood like this, and I'm trying to separate points that are in the next biggest stratum. Okay, and so the issue here is that I know that why not is algebraic, and I know I have global sections that separate points on why not. So, those being algebraic sections, they will exist in a neighborhood that looks like this, but these 2 points don't lie in why not. They lie in the stratum, and so it might be that those sections that the algebricity gives me just all vanish along y1. Okay, so that's sad, but what saves us is that we know. So let's forget this problem for a second. Just these 3 together actually allow me to put an analytic structure on why not union y1. Okay, so these 3 together are enough to make y less than or equal to 1 analytic. Right? Because I can, those 3 scenarios are the only ones that arise if I'm just trying to glue y1 to why not. Okay. So I'll write down the actual string of implications in a second, but the idea is that I'm going to inductively algebraize. Like I'm going to start with why not. I'm going to add in the biggest stratum, y1. That has an analytic structure by what we just said. If I can algebraize it, then as soon as it's algebraic, as if why not union y1 is algebraic, then this problem is going to be solved, right? Because once again, that means there will be algebraic sections which separate points above y naught and y1, and that would mean that this situation is now okay. Okay, so now let me get to the punchline. The punchline is, I'm going to lose the diagram now though because I did this poorly. But if I take any, let's inductively assume that I have algebraized why not union the first I boundary strata starting from the biggest ones. Okay, so if this is algebraic, then as I was saying before, we know that the global sections of the Hodge bundle separate all the points above y less than or equal to I. Okay, and that combined with step 2 means that we can add the next biggest stratum and give it an analytic structure. Okay. Now, what we would like to now say is that we can algebraize that, because then we can close this loop, right? As soon as this is algebraic, then we can run this argument. But this is now some non-compact non-compact analytic space. So we can't use GAGA or something to algebraize it. And this is where kind of this is where O minimal GAGA comes in, which I haven't really talked about, but there's this whole side of this story that uses sort of techniques coming from O minimality, and the long and the short of it is, as long as the kind of functions from which you're building your analytic space are tame in an appropriate sense, it allows you to it gives you a version of GAGA that works for non-compact analytic spaces. So the key words to put here are that this y less than or equal to I plus 1 is not just an analytic space, it's a definable analytic space. It's analytic, it's definably analytic in some O minimal structure. And then by O minimal GAGA, which was proven in the same paper, that does imply that this is algebraic. And so then you can run this loop, and by induction you deduce that the whole image is algebraic. And like I said, now you apply Nakai-Moishe-san. Okay, so just to summarize, the key input from O minimality is, you use Hodge theory to make some nice definable sections, along each strata, but which aren't enough for you to give the whole Y in analytic space, but are enough to sort of add the next biggest stratum one at a time. And then in each step you algebraize and then use the machinery of Hodge theory to upgrade those local sections to algebraic sections, which exist in Zariski opens, which are much bigger. It's basically how you sort of get around the complicatedness of the local topology. Okay, so as promised, I don't have much time to talk about theorem 3, but I have a minute, so I can say something. And the kind of key point, so remember, theorem 3 is telling us that if you consider a variation of Hodge structure coming from the middle cohomology of the family of Calabi Yaus, you want to prove these two conditions. And I can at least draw a picture. The point is that oops, oh, I don't have a picture. Thought I had a picture. Well, let me just say in two words, the main point is that when the Hodge structure degenerates, you get this whole limit mixed Hodge structure. There's a piece of it that contains the Hodge bundle, the smallest piece that contains the Hodge bundle that lives in a certain weight. And the main thrust of the argument here is there's a geometric piece of the degeneration that gives you that piece of the limit mixed Hodge structure, and that's what's called the source. And so the fact that the relevant piece of the limit mixed Hodge structure is coming from a certain geometric piece of the degeneration allows you to use geometry to say something about what that piece looks like. And okay, well, I can tell you more if anyone's interested, but let me stop there.